So the title of the talk is Deep Learning for Visual Traffic Analytics. So it's not exactly what is specified in the agenda, but slightly different, but broadly in the area of visual traffic analytics and the use of deep learning for that. Okay, so before we get started, just to get a sense of the audience, so how many of you are familiar with, say, neural networks? Okay, few people. For others, for example, are you familiar with, say, how one could do, say, an application like object recognition, maybe like bag of words or the traditional methods, maybe not using deep learning, but using something more traditional, at least some familiarity possibly. So I will be starting from scratch. So it's not that I'm going to assume a lot of things, but at the same time, given the background is quite diverse, it would be good to have what do you say, not get into depth of one particular topic, but give you an array of topic. But then the methodology is going to be using deep learning. So I will introduce deep learning in a more rigorous way, rigorous in the sense at least much more than just a black box type, right? And then we will talk about, say, some of these visual recognition problems which are required for doing traffic analytics. So the way, so we have 45 minutes, right? So we have only 45 minutes, so we may not be able to get into a lot of depth. So you understand, right? So I'm going to talk about at least 7 or 8 topics, but not in a lot of detail, but at least some detail which will make you feel that, okay, deep learning is not a black box and it can be used in these applications. Okay, so the way we're going to organize the talk is, first we're going to talk about traffic analytics, just a couple of slides, what sort of applications we are talking about. So it's not about solving all type of problems, slightly specific problems, and we call them visual recognition problems. And we would also talk about the transition from, say, machine learning to deep learning, what it means, and then we will talk about the deep learning solutions. Okay, so this is the overall organization of the talk. I've also kept the slides fairly visual so that you will be able to get a sense of it even if you don't follow the details. Okay, so here is one possible application. You have a camera which is an infrastructure camera, and it is looking at a scene like this, and it can be from a top view like this, or it can be from a much more closer to the land, and you are seeing some sort of sideway movement of vehicles, people, and you have a video, right? And you might be interested in getting counts of objects. You want to recognize what is a bus, what is a car, I mean, is it a person or not? And maybe if you have a video, you also want to reason about, I mean, you want to track the people. Maybe you want to track a vehicle and see whether the person is following a rule. Maybe you are not supposed to take a U-turn at a point, but then the person is taking a U-turn, right? So can you track a vehicle and be able to reason about they not following rules, right? Applications of this nature. So you have to recognize what object is, also track an object maybe in a video, and also maybe reason on top of that, right? These are the kind of applications that we are looking at. So this is one type of problems, right? And also maybe slightly more detail, we might want to even segment the region of a particular object. So for example, this region corresponds to a car, this is another car, and there are multiple cars here. and maybe we want to also detect, say, the number plate. Where is the number plate? Put a bounding box around the number plate, and also maybe find out what is the number, right? Recognize the what is the plate number, right? We want to recognize, and maybe do other things as well, right? But then from this image, the interesting thing is to not just put a bounding box and say that this is a car. We also want to know which pixels correspond to car and different cars. This is the first car, this is the second car, and so on. And also we want to put a box around the number plate, recognize what characters are there, right? So here we are talking about a bunch of problems which we want to solve. Recognize object, track objects, recognize number plate, recognize what is a character, and also every pixel we want to mark it as say a region belonging to, say, an object, right? So this is what we want to do, right? And how do we go about doing it, right? So we have just now defined the visual recognition problems we want to solve, right? And now our tool is deep learning, right? Now we just want to know more about what exactly is deep learning, right? So that is our next topic, right? So that we can go to the third step, which is to solve these problems, right? So first let us know about the tool that we are going to employ, which is deep learning, okay? So what is, so any guesses? I mean, what is deep learning? If you were to answer it, say, in a couple of sentences, what is deep learning? Of course, from an application point of view, you are seeing very good performance. You are able to detect objects correctly, you are able to segment the object correctly thanks to deep learning. But what exactly is deep learning? Any guesses, any answers?
It's a part of the unsupervised classification.
Is it necessarily unsupervised? Deep learning? Is it necessarily unsupervised? Need not be, right? It can be supervised as well. Is it related to neural networks?
Yes, kind of.
It is related to neural networks, 100%.
Kind of.
Kind of.
Neural networks come under deep learning.
It's
Deep learning may have others also.
Yes, yes. So deep learning, I mean, might include other methods as well. For example, deep graphical models is some other method, not necessarily deep neural networks. But yeah, so one instance of deep learning is deep neural networks. So we are on the same page. So we are talking about deep neural networks. So from deep learning, we just move to deep neural networks. What are neural networks?
Kind of replication of human way of learning.
Okay, so that is the inspiration, but as a model, as something that is a computational model, what is neural network? What does it involve? Some input and output, yes, right? And what is happening in between? Yes, there are some layers, yes. Are those layers non-linear layers or linear layers? You have a set of input, you just linearly combine them, and then can that be counted as a neural network? We need non-linearity there, right? So it's non-linear to begin with. Neural network is non-linear. So you have what are called the hidden layers, yes, where there is a non-linearity. And then when we put deep there, what does that bring in? Extraction of features, that is, yeah, I mean, that is there. But just to a neural network, if you add the word deep, what does it bring to the table? More number of layers, right? Instead of just having, say, one layer, you might want to think in terms of, say, 20 layers, 30 layers, right? That is one aspect. But then what that allows is what used to be what is called the feature engineering. Now you can even extract the features using a deep learning network, right? So you introduce more layers, and you also expect the layers to do two tasks. One is the modeling task as well as the task which is to extract features. So we'll come to it, but at least, I mean, we have some understanding. So this is a neural network. right? What does this show you? So you have a bunch of input, you have some weights and bias, you take linear combination of it, apply a non-linearity, right? And then again combine this and you can compute something, right? So this can be used for what is called classification or regression, but then this is the essence of a one layer neural network, right? Linear combination, non-linearity. If you don't have non-linearity, what is the point in having so many layers? You can just have one linear unit, right? So it makes sense to have multiple layers if only you have non-linearity, right? So these are non-linear models. Linear models are simple. You want to have non-linear models, and you also want to have deep non-linear models, which allows you to have what is called a hierarchical structure, right? So you can have hierarchy in terms of a more abstract concept can be at a higher hierarchy, whereas less abstract can be at a lower hierarchy. We'll come to it, but so when somebody talks about deep neural network, the 2 points to remember is there is a hierarchy and then there is nonlinearity. These are two important concepts, right? And here you have a very simple one hidden layer neural network which is doing regression, which is to predict some continuous value. You are trying to have this as input, two numbers go as input, and you're trying to compute, say, a continuous value, right? And then you have what is called the training data, right? Where you have f of x as well as, there is a actual value, which is your what you need to correctly predict, and then the model computes something, right? And based on the difference, which is the mean square error, you compute a cost, right? So your current model, it has these weights, right? It has these weights, and if you are able to minimize, say, this cost, and you have what is called a backpropagation algorithm and change these weights, your model, you can start with a pretty bad model in the sense randomly initialize the weights, but then thanks to this fact that you have a cost function and the backpropagation, you can learn the weights. And this is for a regression problem. Similarly, you can use it for a classification problem. In a classification problem, maybe you want to, you have a binary classification, say whether somebody is, you have a photograph, you want to predict the gender of a person, male or female, right? And your model is saying something, right? And it is giving a score between 0 to 1, but then the actual gender could be 0 or 1, right? And then if you can have a way to measure how much is the discrepancy, which is maybe a cost function, you can backpropagate and learn the weights, right? So this is a simple neural network learning the weights, right? Now, where we get into challenges is, as we just saw, if you have one hidden layer, things are a little easy to handle, but then when you have, say, 20 hidden layers, right, your cost function can look very complicated, right? And we are seeking, say, the minima of this cost function, but then we could be stuck at multiple locations, right, where you don't want to get stuck. You want to go to this minima, right? And so that is one of the challenge with training deep neural networks, right? And a lot of algos and efforts are there to speed up the neural network training and also reach the good minima, right? So this is the background stuff. So any questions on this so far? So we understand what we mean by deep neural networks, right? Neural networks with more hidden layers, and all the weights can be learned using a backpropagation method, right? As simple as that. So now we have a tool where if you can pose a problem as a classification problem, then we can actually find the weights, right? So any questions so far? Now if you have an object recognition problem, right? You want to recognize an object, you want to give an image as input, and you want to give as output, say, not binary classes, but say 20 different classes, right? We can try and use this network, right? As long as an image, you can convert it into a vector, right? If you can convert an image into a vector, right? Now you can classify the object as say one of 10 classes using this neural network, and everything is here. I mean, from here you can just write a small program and you will be able to recognize that whether it is one of these K classes, right? So we can start to solve an object recognition problem if only we can define what are the features. If we can define the features, we are done, right?
Just to link it physically, whenever there is a problem, let's say, comes in front of you and you have to provide an AI solution, to think that, probably deep neural networks will be required to solve this problem. What is that that helps you? Or maybe basic machine learning is enough, or we have to go into that?
I mean, it's not very expensive to try out a deep learning solution. So you can try, say, a traditional method and a deep learning solution.
You're increasing the accuracy.
Yeah, you can increase the accuracy. You might increase the model complexity. You might increase the amount of time taken to train the model. But in your application, if that performance is helpful, you use a deep learning model. I mean,
I want to give an example. At the airport, when you enter, you take your suitcase, briefcase. Nobody checks you there. They just check your normal identity, and thereafter you're inside.
yes.
Let's say we have 3-4 sensors there,
Mm-hmm.
and it's looking at that suitcase. Maybe there's a thermal sensors
Mhm.
it's giving you. You have to identify
Mm-hmm.
not the object basically, but what kind of material.
Okay.
Taking the thermal signature.
Okay.
So this kind of a solution will certainly need neural networks.
Yeah, I mean, I would say the question is for, I mean, a neural network is a more powerful model, right? It is not just having one layer. If you have one layer, like here, how many parameters are there? You have, so you have this as one set of parameter, this is one set of parameters. So you have a set of parameters, right? Suppose say there are 6 parameters. Now if you have a deep neural network, you will have more and more parameters. You will have millions of parameters, right? And to learn millions of parameters, you need tens of millions of data points. So if you can afford to do it for your application, then it makes sense. Otherwise, if you don't have enough data, you get into what is called an overfitting issue, which is it will work on your training data set, but it won't work in the test regime, right? So the choice is, if you have enough data, you can go for a deep learning model, okay? So that is sort of the main key thing. It's a good question, yeah. Okay, so in terms of the visual recognition literature, right, when exactly an important transition happened is 2012, right? When there is a task which is called it's a competition, right? It's a large-scale visual recognition competition starting 2010, and the task is like this: given an image, you have to tell what is the object, right? Here it is a container ship, here it is a motor scooter, and so on. As long as your algorithm, if it returns say 5 title to this image, as long as you get your right answer in one of the 5, you are doing good, right? This is what is called the top 5 accuracy or the top 5 error rate. Here it is the error rate. Top 1 is you should get it right at the beginning, right? And here you see what happened exactly in 2012. A method or model called AlexNet was proposed, right? And they showed a huge improvement in terms of the error rate, right? So it's not accuracy, it's the error rate. They managed to reduce the error rate by quite a big margin, right? So which sort of created ripples, right? I mean, usually people work on say few percent improvement. Here you see a huge jump in the improvement of the performance on this task. So this data set is actually a huge data set. I mean, it's really, really huge, right? And what used to be the approach before was somehow you do what is called feature engineering. Given an image, you would engineer and get some features, and then you have a simple one-layer neural network or a support vector machine or a logistic regression, a simple model here, right? Whereas you would do what is called the feature engineering, right? So I'll give you a motivation, what sort of features would be good, right, for solving a problem like this, where you have cars on one side, on non-car on other side, or aeroplanes and non-aeroplanes as a task, right? So here if you see, when you talk about aeroplanes versus say not aeroplanes, there is a lot of variation in terms of how an aeroplane looks, and even one aeroplane, when you capture a photograph of it in different conditions, different lighting conditions, different angle, it is going to be very different. But what we want to do is, we want to pick any image of say an aeroplane and always say, okay, aeroplane, 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 right? This is what we want to do, but then it looks very, very different, right? But as humans, we know all these are aeroplane. There is something that is common, right? And then something that is different, but we want to always say this is an aeroplane, right? And so one of the idea which is a traditional idea is to do what is called a bag of parts representation, where you have a bag of parts, and you would like to represent say any object, say a face, as 2 eyes, 1 nose and a mouth, right? If you can do that, if you can have a representation where you have the count of the parts, the number of parts, then you will be able to have a model which sits on top of it, which is an easy thing to do, right? As soon as you see, okay, 2 eyes, 1 nose, a mouth, you say it's a person, right? And similarly, you can classify different objects, right? And this used to be the traditional method of somehow feature engineering, right? And the important task, I mean, to solve this is to somehow be able to get the notion of what is called a part, right? So if you can somehow see a image of an aeroplane and get what are called interesting points on an aeroplane, and be able to map all these into one part, which is a tail of an aeroplane or a nose of an aeroplane, right? If you can do it with so much of variation, right? If you can do it, then we can solve the problem of modeling, right? So the traditional approach used to be that somebody is going to design these features, right, so that you will be able to get a representation, and once you have this representation, then you can classify. This used to be the traditional approach, but then when AlexNet came here, right, it was not the approach which is feature engineering, which is what we saw before, right? And some of these methods which were the winners, they were based on that method, right? The bag of parts type of method. Whereas here you see, this one is referred to as feature learning. It's not feature engineering, but it is feature learning. And what is the sort of the idea? The idea is don't do the following, which is you have an image, then you have the feature engineering and you get a vector, and then have a neural network, small neural network, or a SVM. Don't do that. What you do is you start with the image itself, and you extract features from the image and start doing the processing like this. But when we say extract the features, we're not saying what to extract. These are still weights, right? Just like in a neural network, you have those weights, right? So like that, this box, you can think of it as weights. A weight which multiplies every element in this image, and you compute some number, right? It's free in the sense, I mean, initially you randomly initialize these weights, but then with time, you will be able to learn, right? So what essentially is happening is you have this big network, and you have the image and the ground truth, and you have some cost function, and the cost function is helping you learn the weights at every layer, right? And in the process, it is actually computing the features as well, right? So this is like feature learning for free. I mean, the main point, as somebody was asking, so you're actually introducing, instead of just few weights which you had before, now you have lots of weights, right? And you need lots of data to learn those weights, right? So here you see a simple architecture, 1998, Lenet. So this was much older, right? This is not 2012, right? So here, this architecture was proposed much early, and this was used to recognize characters, and here you see the idea of convolution, subsampling, and so on. So that is already there, right? And where the most of the computation really happens is the convolution, right? The convolution is what we described here, right? You take a combination of the you take a weighted combination of the image and you get some number. So this is referred to as convolution, right? And that is where the bulk of the computation happens, right? And you also have what is called a fully connected layer, which is coming later. So the convolution part, what is interesting here is you only take a local combination. You don't take a combination from all the parts of the image. You just do a local computation, right? That is convolution. Whereas a fully connected layer, you have n cross n, all weights are being computed, right? So this is how what is called a convolutional neural network looks like, and this architecture is fairly old, right? And it had so many number of layers. You had this input, and you had a convolution layer, what is called a pooling layer. I mean, these are little details, we'll not get to it, but yeah, so multiple convolution layers, and then what is called a fully connected layers, and you have so many layers already, right? So this used to exist already. What is different now, you see, you note the number here, 32 cross 32, small image, and a character recognition problem, right? Whereas now we are getting into AlexNet, where you have 224 cross 224, and you're able to map it to, say, 1,000 classes, right? In fact, for the AlexNet, you have 1,000 classes or categories that you're trying to classify, right? And a few more additional ideas came in. For example, average pooling was replaced by max pooling, and there are some interesting regularization methods called dropout and so on. But essentially, it is sort of similar, right, what we had before. And the nonlinearity also has changed. Before it was tanh and so on, whereas now you have a faster nonlinearity, ReLU, which makes things a little faster. But it's not, I mean, even if you use tanh, you will still get the results, but then it will take more time for the algo to converge, right? So the point I'm just making is, thanks to say let's say machines which can handle this, right? So the first time that this was implemented on a GPU, it had 60 million parameters, right? It had 60 million parameters, and it required a clever programmer to use 2 GPUs to store these 30 million parameters and do the computation. And it took 5 to 6 days of training time, right? And what is sort of interesting and satisfying is, as we saw just before, compared to the feature engineering approach where we try to extract, we engineer the features, here we have left the network to learn the features, and it is learning something very interesting, right? It is almost, in the initial layers, it is learning about the edges and so on, but later it is starting to learn something more like the parts that we talked about, right? Part of an object, say eyes, nose, and it's more complex shapes. So simple shapes is being sort of learned in the first few layers, whereas more complex shapes are being learned in the later layers, right? So, and with time, what has happened from AlexNet, we have only had improvements, right? What started here with multiple innovations in the architecture, we see that people are starting to claim in 2015 itself on the object recognition task for ImageNet, we have beaten the human level accuracy, right? So as you can see, just the performance in terms of numbers, it's just getting to really, really good levels, right? And as an implementer or as somebody who's building the system, you will take more time to train the model, you need more data, and during testing, you have a little more longer network, right? Multiple computations need to be done to give the output, so it might take some time. You might do some optimization there and so on, but it's not very different, right? In terms of testing, you just have few more computations. Training, you might take more time, right? So these are points to remember, right? And there are multiple innovations that has happened in the architecture, right? People have come up with newer and newer architecture. For example, ResNet 2015, this bet the human performance and so on, right? So we don't have time to get into all details, but yeah. So at least we know how to solve object recognition problem using deep learning, right? And there are a bunch of other problems: object localization, semantic segmentation, instance segmentation, which sort of followed. I mean, once people started doing well on the object recognition task, they started to look at other problems as well, and these other problems are also very interesting, right? So how do you do object localization? What do we mean by object localization? It's not a small image and you want to say what is the object, cup or cube, but you have a large image and you want to tell where the object is, right? You want to localize the object, and so this was the first approach for doing object localization. Given a large image, you do what is called an unsupervised region proposal extraction, or finding out regions in an unsupervised way where could there be an object, right? If you can somehow come up with, say, 2K or 2000 proposals, then you can run a CNN and find out where, what the object is, right? 2000 proposals. For each proposal, run a CNN, find out what the object is, right? So this was, say, early 2013, where you have this unsupervised way. You might have seen such methods where you do the segmentation, fine-grained segmentation, and this can give some proposals, and then you can use those proposals to find out what the object is. Later, what happened? People started to think, okay, let's try to optimize. Why do you have to run the CNN 2000 times? We can do some optimization, right? So they try to do some optimization where they first compute some features and then use the region proposals to simplify things, to simplify the overall computation. That was the first approach. The second approach, people said, why do we have an unsupervised region proposal idea? Where the object could be. Why don't we make it supervised as well? And they proposed what is called a region proposal network. And this was sort of a very good benchmark, which is called the faster RCN. If somebody wants to do object detection, if that is your goal and you want to do it fairly accurately, you want to look at faster RCNN, right? It's a reasonably good approach. But then if you are having a requirement where you want to do it fast, really fast, it's not, faster itself is fast, but then if you want to really make it faster, you might also want to consider what is called YOLO, which is you look at the object only once, right? Here there is no concept of region proposal, so you don't have a part initially where you're finding out where could be the object, but then you divide the whole image into grids, right? And each grid you say, okay, there can be two objects present in one grid, and then you automatically start predicting where the object is. So this is as much I can say at this point, because in the interest of time, right? But definitely look at YOLO, and there are versions, YOLO V1, V2, V3, and the V3 is possibly the one I would recommend. It's very good in terms of both accuracy and speed. How much time we have? 10 minutes? Yeah, okay. So this is object localization, right? Next, let's quickly talk about semantic segmentation. So semantic segmentation, how did people approach this problem? Before the deep learning era, you might have MRFs and CRFs, and that used to be the approach, right? If you want to give a per pixel label, whether that pixel belongs to this object, that object, and so on, you have to somehow consider the dependencies, right? When you say a particular pixel is belonging to an object, the nearby pixels would also be belonging to that object. More likely that it will be the same object, right? So you encode all this using a graphical model, CRF or Markov random field. That used to be the approach. Whereas now you see a slightly different approach. How are people approaching it? You put a neural network, right? You just put a neural network, you have an image, you know what the object is, right? We know how to do it, right? We know that in this layer, we know what the object is. Maybe it's a dog, right? At the same time, here you extract information about the edges and so on. So you have information, very good spatial information that is present here. And here you have the semantic information about the object, right? And if you can somehow make use of both the information, right? And start to, expand. Just the opposite of this convolution is what is called a deconvolution, or you can reinterpret it as some sort of interpolation, right? You have the class information, but then you also have an interpolating network, right? Where, so convolution goes like this one goes like this. So it's a interpolation. So interpolation is again linear combination, weights and so on. So you can learn those weights, right? So you can learn to interpolate, right? If you can learn to interpolate, you can go from small to big, and you can predict at every pixel what is the label, right? What is the class label? And see here, this is a structured task, right? You have pixels. If this belongs to a person, nearby pixels will also be humans, right? Somehow that structured task is handled through a network itself, right? You have a big network which is able to do semantic segmentation, put a label to every pixel, right? And people have extended this, and we have also what is the instant segmentation using what is called a mask RCNN. So we talked about the faster RCNN, which can detect objects. Now you combine it with the semantic segmentation idea, you can also start to put different colors, right? You know that these are all humans, but you also know now that this is a different human, this is a different human, because you can detect a human, right? If you can detect humans and you segment them, you can actually separate them as well, right? So you can also say, okay, these are different instances. So you can go back to the image that I showed before, where you have different cars. Now you can put labels to different cars. You know that this is car 1, car 2, and so on, okay? So maybe applications, right? You can segment people, you can count, and so on, or you can look at traffic conditions, you can detect objects, you can start to even track objects. We'll come to it in a minute, but yeah, at least detecting objects, right? There's a bike, there's a car, you can keep count of objects and so on. So these are things which we can directly start doing now that we have this background, right? And we can detect number plates. It's yet another task, right? Number plate or not, it's a task. If you can have label data for it, you can start to train a model to do this, right? And here, this was one work where you have a camera which is facing the road, and you want to estimate the forward velocity and the angular velocity using, say, a deep learned network, and we wanted to see whether you can predict if somebody is driving rash or not, right? You can do that. Okay, tracking. So I'll quickly touch tracking and one more topic, and then we'll stop. So what is a more traditional way of doing tracking is, say, Kalman filters and particle filters. That used to be the traditional way. When deep learning came in, a first approach that people started to do was what is called the single object tracking, where you have a current frame and a previous frame, right? And you're just, you have a search region or a box which is available, and then you want to match what is the closest in the next image, right? So which is like an image matching. So this was a first approach, which is single object tracking. But more recently, we don't do this so much. We for applications of interest like traffic analytics, we do what is called a multi-object tracking. What do we mean by this? We have very good detectors which can detect objects in every frame. What we need to do is just associate and say, okay, this is the same object here, and so on, right? If you can associate, then we can do multi-object tracking, right? And this is just an example where you have, say, these two images, and we extract features from every bounding box, and it's a matter of matching them, right? And associating them so that you make one-to-one mapping and you can transfer the label ID, right? 1855, 1855, right? You can find the similarity, affinity. This is called the affinity matrix, right? You can propagate the label. So this way you have tracked an object or tracked a person, right? And this need not be just for two objects. It can be multiple objects, right? And so this is a very early tracker that came where you have this. So this is, I mean, our implementation of it where we have used YOLO v3, run it on 2 frames. You get these bounding boxes, right? And from here, you can use the Kalman filter to predict where the bounding box will be in the next frame. And you just use the affinity matching to find the correspondences, right? As simple as that. I mean, you have detectors working with the Kalman filter, you can track an object very easily, right? So there is one limitation of this. It doesn't consider so much. So here, this Hungarian algorithm mainly uses what is called the IOU or the overlap between these 2 boxes. It doesn't consider what is the appearance of the object, right? So that was one extension later, which is what is called a deep sort. The previous method was called sort. You can extend it to deep sort, where you not only look at the location, but also the appearance, right? You want, if a person is here, a person is here, the appearance will also be very similar, right? But what is the main point? The main point is the detectors have become very good, exploited to track the objects, right? So this is the main point. And last, wanted to talk about scene text recognition. Suppose you want to do number plate, you have detected the number plate, now you want to read the number plate characters, right? This is the problem that you want to solve. And structured text is fairly easy, right? When it is a scene text, it is quite complex because there is a lot of variability, right? Scene and character font and so on, right? So traditional approach, apply filters, contour detection, image classification. This used to be the traditional approach, right? For example, you might have seen these, right? You do some pre-processing, detect the number plate, and have a classifier, SVM, number plate or not. And then once you have detected a number plate, then you do some thresholding, find some contours, and then run some character recognition on top of it. This is the traditional approach, right? But then, thanks to the deep learning models, right? So how people approach this? Let's do a very quick text detection, right? So this is one I would recommend you to look at this EAST, which is a quick text detector. So here you see the outputs, right? You can very quickly detect text. Wherever you see text, you can detect the text. There are some extensions of this as well, but essentially you have a deep neural network doing the job underneath, right? That's the network which is there. You detect the objects, then so this is a slight variation, I'll skip it. So once you have detected the objects, suppose you have this as an input, right? Now you want to get the characters as output, right? So this is also same as similar to a speech recognition problem, right? In speech you have a waveform and you want to get characters as output, right? Here also you have image, you have the characters there, and you want to recognize the characters, right? And just in speech, like in speech, there is a idea which is called the connectionist temporal classification, CTC, if somebody is interested. So this was a big breakthrough in speech where you could use this idea to do the transcription, right, from here to here without doing what is called alignment. You don't want to know where exactly is S, T, and so on. You can take this whole thing as input and be able to predict what is the output, which is the characters, set of characters, right? And much more recently, what people have tried to do is, I mean, don't break it down into 2 steps. So here we have the detection step and then the character recognition step. People have gone beyond this, and this is a method called C, where they don't even do the detection as a separate task, and they do what is called a end-to-end. So this is a new term in deep learning, which is do an end-to-end, in the sense you start from here and you have only ground truth in terms of the words that exist, and you learn along the way to predict the bounding boxes and also to predict what characters are inside, right? And so here you see this is the image, and you're able to get the bounding boxes of the object, the scene text, and also start to predict what is the characters which are present, okay? So I thought I'll stop here. I mean, you have a flavor in terms of what exactly is machine learning and what problems can be solved, and at least some starting points to solve some of these problems, okay? So is good time? Yeah, thanks.
Thank you, Dinesh.
There seem to be some.
I just wanted to know, like, whenever you are deciding the UKV network, does the number of layers or hidden layers, do they have any physical meaning? Because number of times you just build the model and it's very hard to
Yeah. So yeah, there's probably no physical meaning. The closest one can probably, I mean, it's an empirical quantity. I mean, it's like a hyperparameter. It's something that people experiment with, and it is very difficult to train multiple models with multiple number of hidden layers and units, right? So people, what they go by is, okay, have somebody solved a similar problem somewhere. Maybe they have a lot of resources. They would have tried their best to get a rough sense of, okay, how many hidden layers to use and what should be the filter size and so on. Still empirical. Maybe you might start there.
It is specific to a specific
Yes.
problem.
Yes.
And also, like in place of having number of hidden layers, we can also go for large number of
Yes.
layers.
Yes.
Is there any trade-off?
Trade-off, yeah. So there is a theorem which says that even one hidden layer, if you have infinitely many, you can solve all problems, right? So there exists in theory such a principle, but then to be able to get to a solution is usually very hard. You are not able to train such a one layer, several hidden unit network to solve a problem. Whereas hierarchical models, you are able to train and get a solution, right? So in theory, it is equivalent or it is as good, one layer itself is as good, but then you are not able to train such a model.
I have a couple of questions. The first one being, going through your entire presentation, it's quite obvious that a person venturing into the area of deep learning and CNN has to be well versed in the fields of linear algebra and calculus. So apart from this, you have any other math proficiency that needs to be acquired so that one is able to develop algorithms and models in this domain?
I think linear algebra and calculus, I think that's good. Convex optimization or optimization, yes.
And my second question is basically, you showed about object detection and multi-object detection in images and frames. So let us say that there is a corridor, let us say example of Indian Institute of Science, the roads. There is a road and through the road we have collected a video. So on either side of the road I have n number of features. It could be assets or it could be trees and vegetation and all these things. So if I take each image per se, I am able to apply deep learning models and try to recognize what all features are there. Can I sort of do a stereo correlation and also geolocate the position of the features I've detected in each frame, so that by just applying this whole model on a video, I'm able to replicate the entire road as a geomap or something like that?
Yeah. So, I mean, so there exists literature which is on depth estimation using single cameras and so on. So I think, I mean, so if one does depth estimation and combine it with the semantic segmentation or instance segmentation information, so you can also start putting it in 3D, right? Where things are. Yes.
It's quite possible.
Yes.
So
Yes.
by just analyzing the video, we can come up with a map of the entire corridor.
Yes.
Sir, you talk about the number plate recognition and the object instance segmentation. By this technique, can you identify the virus?
Virus?
Any virus that is spreading in the China.
Uh-huh.
This type of things is possible, but
No, it's not related.
it is not right.
It's not related, yeah.
So what is the input required to identify these type of things?
So here it is a simple image recognition problem, right? I mean, there exists literature on medical image segmentation or recognition and so on, yes. But yeah, I mean, one has to look at what is the closest thing. Maybe, I don't know, is it blood sample or is it,
Coronavirus and other virus is just spreading.
yes.
And this technique can help us to identify it.
I'm sure, yes. I mean, if you have the right data set and you have the right ground truth and input image, yes. But yeah, in principle, yes. I mean, I think a lot of details have to be worked out. Okay. Yes.
So, in terms of deep learning and all these models, we are talking about embedded models, as in which can be deployed in field, in small devices, glasses, or something like that. So, if the model is so complex and takes so much computing, do you think we can do the computing on a PC and then just embed it in a less powerful device?
So so the inference procedure usually is fairly simple, which is feed-forward operation. But there exists a body of work where you try to reduce the number of parameters. For example, you have 60 million parameters, say in AlexNet. So there exists works where they said, can I reduce the number of parameters using some ideas, but then don't lose a lot of performance. And there do exist, for example, you can do a 50x reduction. From 60 million, you can do a 50x reduction or even more reduction in terms of the number of parameters, yes. And a lot of work happens in that space. We couldn't cover it, yes.